speak here. What I want to talk about today is part of an ongoing project with my collaborators, which has to do with applying ideas from homology theory and higher categories to the Langlands correspondence. So first, let me say, let me just what we're talking about. So Langlands correspondence. And for today, it will be these ideas are useful in more generality than in other contexts as well, in more generality than this, but I think the cleanest formulation is in this setting. So we have a smooth and proper curve. For a finite field. Closure. Zero. Well, so what's the Langlands correspondence about? Well, roughly speaking, correspondence are forms. Order, which for us will mean something like the big group. So let me just say a few words about what these objects are, and if these are not familiar, don't worry. So first of all, so this big group. So this is approximately the entire fundamental group of the arithmetic curve. Langlands duality. Well, the theory of reductive groups. Well, they're essentially determined by combinatorial data, and there's a duality among this combinatorial data. This is how one obtains the dual group. So like automorphic forms, there are various ways of saying it, but what I will mean is the following. Yeah, so you can build the moduli space of principal G bundles. Compact supported functions from of this moduli space to, well, whatever our coefficients are, which is Q bar. So now here is some prime different from P. The coefficient here. So roughly there should be some correspondence like this. Again, let me say for the time being, if these look unfamiliar or a little bit scary, don't worry. For the first part, I want to kind of try to use this as motivation to describe kind of a general principle that's much more widely applicable, that's independent, a little bit independent of the specifics of this situation. For starters, so I drew this squiggly arrow, and part of the reason I did that is this is a very imprecise state. Well, first of all, I stated it particularly in an especially imprecise way, but even if you look at kind of carefully at the relevant literature, it's not exactly a precise conjecture. This is not meant to be a one-to-one correspondence, for instance. In good cases, this is supposed to be finite to one. And in general, it's kind of a difficult problem to in some sense even formulate a very precise conjecture of what these things. For instance, what one might want out of a precise conjecture is how to describe automorphic forms purely in terms of the Galois. And that's not something classically available. But anyway, so the kind of a very general idea I want to try to apply is what's called categorification. Let me say, so now for the moment, forget everything about the word Langlands. I want to explain what I mean by this and how it plays a role in arithmetic geometry. So there's a hierarchy of categories, starting with -1 categories. One category, 0 categories. Categories. And hierarchy. So what do I mean by -1 categories? I mean like a number is a -1 category. A single number or a single function regarded as a -1 category. So the way these are kind of related is that an element of each previous one can be thought of as an element of a kind of the next one. So 0 category is something like a vector space. So this is where a function might live in a vector space of functions, and so on. So similarly, vector spaces form a category, categories form a 2 category, and so on. And so there's a general idea that it's often, if you want to study something like a number, it's often a good idea to express it as maybe the Euler characteristic of some chain complex. So vector space would be in a more general sense a chain complex. So maybe the first instance of categorification comes from topology. It was an idea of, I think, Emmy-Noether that suggested that rather than studying the Betti numbers of a topological space, one should instead study the homology or the cohomology. And this has real consequences. So two important consequences of this idea, even in topology, is the theory of characteristic classes, which would be impossible to state because those are elements of cohomology groups, and the Lefschetz fixed point, which looks a little bit like an alternating sum of Betti numbers, but it's an Euler characteristic it's a trace of a different linear map acting on cohomology. So this kind of extra freedom of passing from numbers to vector spaces allows you to do this. And so the idea is to kind of go further in this hierarchy and leverage this. But before I do that, let me try to explain how even this passage from -1 categories to 0 categories happens in arithmetic geometry. So in arithmetic geometry, one typically studies the following problem. So one has, suppose I have some variety and the field, and again, y will be this. So the way to relate, so there's a standard idea in this business is to relate y, which is kind of an object which you can study using methods of more topological methods, to y0, which is that there's a Frobenius, there's a certain endomorphism of y, such that the fixed points, these fixed points is exactly the FQ points. So leveraging this kind of a standard idea in this business, and so in other words, the dynamic of the Frobenius homomorphism is exactly the arithmetic of the algebraic variety. And so they had this idea that there should exist a homology theory. For varieties. Or, in particular, with the Lefschetz then one could apply it to the Frobenius automorphism. And then one could, and then one could take this homology and evaluate the trace of Frobenius acting on this homology to get a count of fixed points. So this is given by a lot of homology. And so what one has is that the number of points is the maybe the trace of Frobenius or homology of Y. And so there's something kind of remarkable already I want to point out about this. Well, one is it gives a kind of a nice formula for counting points. But it has the fact that such a thing is true already has interesting consequences. The point. For instance, it means that as a function, the number of points is a function of q. Q is a power of a prime. So as a function of the power, this is a kind of regularly behaved. It's trace powers of something acting on a vector. For instance, there's a way of packaging this information of counting. There's a generating function for a number of points, which is the zeta function, and this automatically implies that the zeta function is rational. More one could say, but we can leave it at that. Also, this is kind of going to be a prototype for the kind of thing we want to do, which is that notice over what was the idea. So we wanted to study a number, which is the number of fixed points in the arithmetic setting over a finite field. What we did is we first associated a vector space over the algebraic closure, and then took trace of Frobenius. The general pattern that I want to suggest is that if one wants to study some arithmetic information, one should go one category level up, assign an invariant of that form to the thing over the algebraic closure, and then use whatever ideas about geometry to understand that, and then only at the end pass to the arithmetic information by taking trace of Frobenius in the appropriate sense. So let me try to explain how this plays out in this kind of setting. So the thing about this lattice homology is that it comes with a theory of coefficients. So we're thinking about this idea of categorifying functions by looking at sheaves. Suppose closure. Let's call it base structure. So what this means is that, well, there's this Frobenius map. And so I want a comparison. So then this defines a function at 2 points. Prove that f points of y. The way it works is that if we pick a rational point, then well, what do we have? We define the value of this function defined as a trace of a certain linear transformation. And it's between the fibers of x. So we take the fiber at y, this maps to the alpha sub y, just using the space structure. But because precisely because y was a rational point. In other words, it's a fixed point of the Frobenius. This is canonically identified the fiber at y. So you take this composite map and take its trace, and that's the value of the function. So this way, starting with a sheaf with this kind of structure, one can take the trace of Frobenius in a slightly more sophisticated way and obtain a function on the rational points. So again, this fits this kind of pattern where to get a function, you first construct a sheaf on the algebraic closure and then take trace of Frobenius. Similarly, so the other thing to say is that such functions also, in the same way, are necessarily kind of have some kind of regularity in this parameter Q. Like such a sheaf doesn't just give you one such function, it gives you a function for all powers of Q at the same time. Okay, so the one key point, kind of getting back, what does this have to do with the Langlands correspondence? Is that typically the way one constructs automorphic forms is via the function sheaf correspondence. You want to write down an automorphic form. A good idea is to write down a sheaf over the algebraic closure of the stack of principal G bundles, and then apply the function sheaf correspondence. Forms. Rise. Apply to just modulate stack of principal G bundles. Okay, great. Now, so now this is great. So this gives a kind of a funny way of categorifying the notion of function to a sheaf of the algebraic closure. So of course, there's a kind of a more dumb way of categorifying function, which is the space of all functions. And well, I mean, maybe one thing to say is that passing in either direction here is more of an art than a science. It's only going to be useful to the extent that the way you do it is a good idea. On the other hand, there's a natural candidate for kind of further categorification, which is supposed to categorify both sheaves and the space of all functions, which is just both sheaves. Rather than looking at one sheaf, you can look at the whole category of sheaves. Further. Sure. So one might be inspired to do this in this setting if, for instance, one naturally arrives at this from these considerations, from trying to answer the question of, well, if I believe in this correspondence, if it should be good enough, then I should be able to describe the left-hand side purely in terms of the right-hand side. And so, well, I want, so I want something which gives me the space, the vector space of all automorphic forms, rather than just one at a time. And so the natural way to, from this point of view, the natural way to categorify that is to use the limit. So this raises the question: what is the trace of Frobenius? This is the it is. So then one is naturally led to contemplate this question, and perhaps one can hope that this would give you automorphic functions, and then we'd be in good shape at least for the left-hand side of this, applying this idea. Of course, nothing yet happened on the right-hand side, and so before answering this question, one has to contemplate exactly what it means to take a trace of a functor acting on a category. So let me briefly tell you something about the abstract theory of traces. So the setting is that if you have any symmetric monoidal category, object, there's a notion for it to be dualizable. Means that there is, well, that it means there exists a dual and certain maps. The other way of the code unit, satisfying some conditions, which are half jokingly sometimes called Zoro's lemma. So because the reason it's called like that is because whatever the condition is, one usually writes it like this diagram. This left-hand side is like the mark of Zorro. So then if I have an arbitrary endomorphism, then I can take a trace of that acting on X. This is by definition the composite morphism. So whatever this is an element of the endomorphisms from the unit, my category to itself. Okay, so this is all very abstract. Let's try to bring this down to earth a little bit. So if you take this category to be the category of vector space, the usual category of vector spaces over a field, then being dualizable is exactly the same as being finite dimensional. So you can check that this is you haven't seen this is a great exercise to do, that this is a basis-free characterization of what it means to be a finite dimensional vector space. And the trace is the usual trace via the identification of the vector space tensor dual with endomorphisms. This co-unit is exactly the trace map for that. So from 1 to 1 is just the base field here. Okay. Vector spaces. So the example that we'll be more interested in is kind of higher up. When we take the symmetric monoidal category to be, well, the category of DG categories, appropriately understood. So this is now objects are categories, morphisms are functors, and well, you also have two morphisms, although those won't play a role yet. And so there's what's kind of non-trivial is that there's a kind of a tensor structure on this category. Don't want to say much about it. I guess, I don't know. I guess I should say one of the upshots of a lot of work in abstract homology theory is now that there's a kind of a good linear algebra that you can do in this category. So in particular, you can study traces. So if I have some object here, the endo functor, well, I can't, in this level of generality, I can't say to you much about what the trace is, other than it has a name. It has a different name, which you may have heard of. Trace F and C. This is the same. This is the Hochschild homology of C with coefficients in this one. So that's just to name it. Another example, which is closer to geometry, is to consider category of correspondences of schemes. So there's nothing special about schemes. You can consider correspondences of anything, and this will work the same. I just wanted to be a little bit more concrete. So the objects here are schemes, objects, schemes, are morphisms. decomposition is given by fiber product. So there's a natural tensor structure here. Well, given by on the underlying things taking the Cartesian product. It's not the Cartesian product in this category. And here, every object is realizable. So the unit is the point, and both the unit and the co-unit are given by the correspondence given by the diagonal. You can read it either this way or this way, and those give you exactly the unit and the co-unit. Now, if you've seen this kind of thing, I invite you to check that this is that this gives a duality data. And so what's the point? So if I have a map from X to X, I have a map of schemes. Well, this gives you a map in correspondence. Or just take the first leg to be the identity. Then I can try to evaluate the trace of this. So first of all, where does this live? This lives in correspondences between point and point. But such a thing is exactly, well, it's a scheme mapping to point and mapping to point. There's a unique map to point, so this is a scheme. Actually form a category, never mind. So this is, let's say, the groupoid of schemes. And so, well, which is it? Well, it's naturally the fixed points. So maybe let me more suggestively write this as it's the fiber product, where one map is the diagonal and the other map is identity comma map. If you trace through this definition, you will exactly find this fiber product, which is a formula for the fixed points. So this looks good. So we might want to. So for instance, if we apply it to the Frobenius map, we'll get exactly the FT points. Great. And so now the key observation is that trace is functorial with respect to symmetric monoidal functors. So what that means, for instance, is so here is a situation where it's very easy to calculate traces. So if I have a symmetric monoidal functor from this anywhere, then I can calculate traces of the resulting ones. Just it will be the corresponding thing. So the good news is that the assignment to a scheme, the category of Atlantic sheaves, is functorial with respect to correspondences. This is great. So this leads to the reasonable expectation. Let me, oops, one. That the terms of Frobenius, all right, that this, well, just applying what you would get, which is the fixed points, and then applying the functor, well, that functor assigns, the way this works is that it assigns compactly supported homology, one way it's applies, compactly supported homology to the correspondence. Yes. So which is exactly this really is functions. So this looks great, except there's a problem. This is functorial, but it's not symmetric monoidal. It's only laxly symmetric monoidal. So if y1 and y2, if you have y1 and y2, is that there's a natural, fully faithful in fact, functor. It's on y1, and search sheets on y2, on the product. there's a natural way to do it. It's called the box product, but it's not. But it's not an equivalence, except in very special cases. All right. So how to fix this? We want to describe the first step. We want to express automorphic forms as a trace of something. So there are kind of two approaches to fixing this. So one is kind of more formal and a little bit weird, but to get to it, it will play an important role at the end of this talk, which is it's a kind of a formal construction. So just this Sheaves is an object of this category. It's a UG category. So just replace the target of what you mean by Sheaves by a different two category. Hopefully somehow related to the original. And enhance Sheaves to underline. So the way this works is that this has a forgetful functor to just categories, and then this is kind of a lift of this functor. And the idea is that this one would be symmetric monoidal, and then everything would work great. So that's kind of one slightly strange formal approach. And the non-formal approach is to replace Sheaves on Y by a different category. Let's not give up on the ambient category for lots of reasons. We like this one. So for most of the remainder of the talk, let me focus on the second idea in the case that we're interested in, which is to get automorphic forms. So specifically for so in this case, we can take inspiration from the Langlands correspondence. So, I said there should be a correspondence between automorphic forms and Gaitsgory representations. It's not some abstract thing that associates one to the other. There's some compatibility. There's some expected compatibility. So it's not just so one of the expected compatibility it has to do with what's called a Hecke action. So, in fact, this is the main place, probably the only place in this talk where the passage from the group to the Langlands dual group happens, which is that we have the geometric Hecke equivalence. And what it does for us is that if you take a point on the curve, for every point, it gives you an action of the category of representations of the dual group on this category of Sheaves. We have this, so that's something that kind of comes out of what the geometric Hecke equivalence is. This is where.
Sorry, so clarify.
Yeah.
In this expectation, your underlying nodal category is cat as a two category.
That's right. Oh no, sorry. No, sorry. This there's supposed to be a forgetful functor here. And so when you apply this, then you remove the underline.
But in this second.
Oh, in the second thing, yeah, you're just purely impure. Yeah, that's right. So it's kind of funny formal idea, but at the end of the day, one wants to deal with purposes of what we're doing. It's important that one actually has a category and not some funny structure.
Under action.
Yeah.
Feeling.
What's that? Yeah.
What does it do with feeling?
So the Hecke action is the following. So it comes from the geometric Satoke equivalence, and what it does for you is the following. For every point on your curve, you obtain an action of the category of representations of the dual group on the category of sheaves. This is sometimes called the automorphic category, and for every point, you get an action of the category of representations. I haven't said that compatibility yet. I want to phrase it in a funny way. So first of all, that you can do this. So this depends continuously on the point. What I mean by this, so vary the point. And so what you get, you get something that looks like this. So you input a representation of the dual group on the G, and you end up with is a sheaf not on bunch G, but on the product of bunch G and the curve. With the idea being that the restriction for every point, the restriction of it recovers this personal action. So this is the sense in which these functors behave continuously with respect to the curve. So now the point is, the expectation is this. So if I have an irreducible the law representation, so what I expect for various reasons is to obtain a sheaf whose underlying function will be the automorphic form, which is what's called a Hecke eigensheaf. So what this means is that stage is some representation. And I apply this Hecke function to it. What it's supposed to be is not some random sheaf on the product, but it's supposed to do the following. You're supposed to take the same sheaf and then tensor it with, well, if you have a G local system, the Galois representation is the same as a G local system on the curve. So given a G check local system, so given a G check local system and a representation of G check, you can form kind of the associated bundle, which will be a local system of vector spaces. This is this one. And so, well, you can take the box prime. This naturally lives in this particular is totally constant. So let me use the word these terms. So these will mean the full subcategory of sheaves on X, which have this local constant property. So this automatically is true because this is a local system. Yeah, exactly. Yeah, so the sigma here is the eigenvalue. Yeah. So taking some inspiration from this expectation, this gives us an idea for how to cut down this category into something that kind of more closely resembles the thing we want. So there's a bit of a leak here. I apologize. But so now what we can do is we can consider the full subcategory here, where with exactly this local constant. Really, an insight here is that the key feature of Hecke eigensheets is this local constancy with respect to the action of the Hecke operators. Consider each L stands for Hecke. So this is here. If this, well, it's no longer a Hecke eigensheet, but I wanted to lie in this pattern. So the idea is that as the point moves around the curve, that the action is, well, up to homology the same. So on type 0 it's the same, but it involves the way it's not the same only involves the topology of X and not the geometry. So this is going to be the kind of the right thing to consider. So this looks a little bit. So one of the things we prove about it is give a geometric description of this, purely geometric description of this category. Is that this is the same as all sheets with something called nilpotent singular support. So there's a kind of a half-dimensional subspace of the cotangent bundle, stack of p bundles, and there's a notion of singular. So given a sheaf, there's something called a singular support, or which is in the Slavic context, it's a kind of a recent development due to Sasha Valens and Hecke Saito, which assigns to one of these sheaves a half-dimensional subset of the cotangent bundle. And so this subcategory is exactly cut out by this geometric restriction that the cotangent vectors are in this. So the reason that this is nice, at least psychologically, is because, well, this description involves Langlands duality, but this nil does not involve Langlands duality at all. And so, kind of structurally, the key feature that's relevant is this Hecke. On the other hand, it's kind of nice to know that it's given by this geometric condition. Okay. So maybe since I mentioned this, one thing to say is that right away, of course, by definition, Hecke eigensheaves are Hecke. So in particular, a very special case of this result resolves a conjecture of Lamont, which says that Hecke eigensheaves have nilpotent singular support. But okay, so the kind of theorem would say something about is actually calculating the traces for Frobenius of this as a category. The theorem says that, well, I'll write it in this nil terms, so that if you take the action of Frobenius, acting on this category, so this is the vector space of automorphic forms. By the way, everything. One part of this theorem is that everything here is, this is the derived category. In particular, a trace is a priori a chain complex. And so one thing that this says is that it only has cohomology in degree 0, and that unique cohomology group is the vector space of automorphic forms. So maybe let me emphasize that unlike a lot of the previous discussion, this is by no means formal. There were some formal reasons to expect that the trace on all sheaves would be functions. Here, this is also reasonable expectations, but this nil create, simultaneously solves this problem that we have with the tensor problem. It creates its own set of differences. So in particular, the proof of this theorem involves Langlands, even though there's no Langlands duality in this theorem, the proof involves Langlands duality in an essential way. So, in the time, let me sort of try to explain what the structural features are. And well, I promised something about, I want to say what consequences all of this has for the original question about saying something new about automorphic. I guess this is a new statement, but one might object, well, maybe I don't care about this, I just care about this vector. What have you done for me? So
Can I just ask, like, in what sense does the Hecke condition help resolve this issue with the tensor products?
So it is true that, for instance, if you take Sheaves on fun G times something, where you impose the condition of being nilpotent support on the fun G factor, then that splits as a tensor product. So it has this. So this is also true for if you look at least Sheaves on a proper variety. So in some sense, this category behaves like the category of local systems on a proper variety. This is kind of part of the thing.
That you put it include condition.
It's not true.
But you get something.
Oh no, I don't think so. I mean, the way to get something reasonable is by doing this.
Well, that's good.
Yeah, is to kind of change what you mean by trace. What's that? It's a little harder to say bigger or smaller.
Later description.
No, I don't think so. It's a mess. It's something not at all reasonable. I mean, there's another reason why this is a good idea, which has to do with the other side of the Langlands. So far, I've just been kind of working on the left-hand side. So now let's consider the right. Let's seriously contemplate the right-hand side. So the point is, I mean, one thing that people have wanted to for a long time is to have a good moduli space of Langlands parameters. You want to parameterize the L-bar representation to fit into some kind of an algebraic stack or something like that. The main source of difficulty is that, you know, this Bay group or the Ital fundamental group, it has a topology to it. And there's no great way of associating an algebraic stack, at least, which parameterizes representations of a group with a profinite topology. And so, you know, now there are a few approaches. So we have one. So our approach is to define space or representations. Our approach is inspired by what happens in the topology. So in topology, well, there's no problem. The fundamental group doesn't have any topology, and you can just look at its character variety, essentially. And the part of the inspiration is that this character variety has a Tanakian description. And so this we can kind of import into this Aladdin world. So let me give it a name. So this is what we call restricted on X. So this is defined as follows. Defined as, well, so these things are defined in terms of kind of a functor of points. So for a test scheme, S, yeah, I should say. So this has the structure of a well-derived but stack. The field of coefficients here is Q bar, which is different from 1G and X. So there's kind of two different types of algebraic geometry. One over a field of characteristic P and one over a field of characteristic 0. So for test scheme S, so an S point, right of representations to, well, quasi-covariant sheaves on S. tensor with this funny category lease of X. So the inspiration here is that in topology, if X was a topological space, and I did the same exact definition, except I replaced lease with the category of all, with the full subcategory of all sheaves which have locally constant homologies, I would get exactly, well, a derived version of the character graph. Here, the difference between kind of the homotropic theoretic version and the ellatic version is that the ellatic version only kind of sees local systems or locally constant sheaves where the fibers are finite dimension. And so that's kind of the main difference here. And from some point of view, this looks crazy. Exactly because of this issue. I mean, it's kind of the smallest possible. In some sense, it's the smallest possible thing you can do because this category is sort of so much smaller. It doesn't let you interpolate between different local systems. For instance, if G is the multiplicative group, then this thing has a component for every representation. So in general, in general, this looks like this splits up as just a disjoint union, as it turns out, over something called semi-simple. So this might look, so this condition of semi-simplicity. So for instance, if the group is the multiplicative group, every representation is semi-simple. And so, well, it looks like, well, on some level, it looks like, well, it looks a lot like I just took the disjoint union of all the possible things. But that's not true. There is genuine structure here. One bit of structure is that for more general reductive groups, you can have different representations with the same semi-simplification, and those get grouped together. And more seriously, there's kind of a stacky structure here.
Sorry,
and
so
a derived
what does
structure.
the sigma mean? Does it mean everything with the semi-simplification?
Yes, everything with the same semi-simplification, exactly. And there's a kind of a stacky and derived structure here, which plays an important role. So maybe we state, first of all, this already defining this moduli space, let's one state a kind of categorified version of the So say it's the equivalent. This well, I want to say coherent sheaves, but certain category of coherent sheaves on this stack of restricted local systems. So let me emphasize that these two appearances of nil are very different. This nil is sort of, for the purposes of this talk, this nil is really important, and this nil you can ignore. They play, despite the fact that this looks kind of symmetric, they seem to be completely unrelated and play totally different roles. So this has to do with what are called Arthur parameters, but I'm not going to say anything about them. So you can just pretend that I said just coherent or quasi-coherent sheaves on this stack. I just wanted to make a statement that's not known to be false. So importantly, this conjecture takes place. So notice the way I phrase this is that this conjecture doesn't involve arithmetic at all. This conjecture takes place purely for the algebraic closure. And so the idea is that if one believes this conjecture, then one should recover the usual kind of thing that you want from the Langlands correspondence by taking the trace of Frobenius of this thing. So let me, in the remaining minutes, let me try to describe what happens when you do this. So a key result here is that, well, we made some progress towards proving this conjecture. So there's a natural action. So if you forget this info nil and think of it as quasi-code, well, these are pretty close. And moreover, this is a modular category. The quasi-coherent shapes on anything has a symmetric fundamental structure and it acts on this category. So what we proved is that there's a kind of a spectral action. Natural action. Quasi-coherent shapes. Sort of compatible with the Hecke action. Not say. Random action. It's compatible with these Hecke operators. So, whoops, no, not true otherwise. False. And so let me say, so the way this is proved is again taking inspiration from topology and homology theory. Is really, in some sense, it's purely a theorem about this category. It's the theorem that we prove is kind of give a universal property for this category, inspired by the theory of factorization homology in topology in these kinds of terms, and that tells you what it means for it to act on anything. And then you just observe that the kind of structure you get from Hecke operators is exactly what gives you such an action. So there's that. So that's great. And so, by the way, what in perfect, well, yeah. So, right. So, by the way, this has a funny corollary. We're taking traces. Funny corollary, which is that this category kind of abstractly defined either in terms of Milton and singular support or Hecke-Lees actually splits up as a direct sum of categories. Precisely because this thing was a disjoint union, then you have projectors on the components in the usual way, and this splits up over the same simplifications of the corresponding. So that's where you start with something connected, and you look at some category of sheaves on it, and it turns out to be just a direct sum of categories. So, I mean, in particular, this has kind of an interesting consequence that if you have two Hecke eigensheaves with eigenvalues that have different semi-simplifications, all the x's between them match. Okay. So is it just that I will subsets? That's right. Yeah, yeah, that's right. But importantly, if you want to split the whole vector space, you need some local finiteness. Like the vector space is infinite dimension. Yeah.
So the fact that there are total is not so surprising, but the fact that some
Yeah, that's right. Yeah, so this is a kind of statement of finiteness, a very strong finiteness statement. So, okay. So now let's combine this action and this conjecture and see what it says about the trace. Which we know if we take trace of Frobenius, we have automorphic forms. So for this, I need a slight enhancement. The theory of what we call enhancement. setup is like this. Suppose you have some monoidal category, rigid. Category, which acts on some modular category. You have an endomorphism here, and you have a compatible endomorphism back, which means that from now well, I should have said that if you have a monoidal category, there's a way to take trace in the world of monoidal categories. And what you get is just an ordinary category. So there's something called, so what you get is, sorry, this gets a little bit, what we call an enhanced trace, which is maybe another word for it is the term class of this FM. Now, lives in this kind of monoidal trace category of okay. So I want to apply this. I want to apply this to my spectral action. Let me apply this to this action here. Action. Well, what I get is a kind of an enhanced trace Frobenius acting on this automorphic category. That's inside this monoidal trace, I said, of Frobenius acting on this local systems. So this, maybe not surprisingly, by the same kind of argument as we did with, similar to the kind of argument I did in the beginning with correspondences, this is just identified as a category of quasi-coherent sheaves on the Frobenius fixed points of the stack. So I guess one caveat is one has to take the derived version here. Since we're dealing with coherent sheaves, it's important to keep track of the derived structure. So this we give a name, which is arithmetic global systems. This is the definition of it. And so the upshot is that this thing produces, so that taking trace produces a certain quasi-coherent sheaf on the stack of arithmetic local systems. Moreover, by this, the theorem about enhanced traces is that if you take the ordinary trace of M acting on M, this is equal to just monoidal trace category. Sorry, this is a little bit of a mouthful from the unit into the enhanced trace. That's the sense in which it's enhanced. And so the point is you have some sheaf, you obtain some sheaf on the stack of arithmetic local systems whose global sections is just the ordinary trace, which, while I claim, is the vector space of automorphic forms. So upshot of a sheaf, we call it graph. So such that gamma of it is the vector is just the vector space of automorphic forms. In fact, it has much more structure than that. This sheaf. So this stack is by no means affine. So global sections is just a small part of it. In fact, this sheaf encodes all the homologies of what are called shtukas in a kind of in a coherent way. It just encodes all of them. And so say things. Just that, well, first of all, the corollary of the conjecture geometric Langlands conjecture is the following: is that this quasi-coherent sheaf can be described very concretely. It's just a dualizing complex of the stack. So at least conjecturally, this gives a purely in purely spectral terms a description of automorphic forms. It's just the homology of the dualizing complex on the stack of Langlands parameters. So that was a restricted geometric Langlands conjecture. So that's one thing. And then on the other thing I want to say is that on global sections, of action. On automorphic forms. And so the important thing about this is that, well, we proved in the same paper that this receives a natural map from Vincent's Lafforgue algebra of excursion operators. It's actually a refinement of it. And so in particular, on global sections, this gives, and the action is the same, so that this gives, so on global sections, get some Lafforgue's decomposition. Forms. So vector space is a direct sum. Simple parts. Fine. And X. Of course. Yes, it's very much a refinement.
So, this fine.
Yeah, that's right.
So
So it's a kind of a localization.
And your theory recovers.
Yeah. Yeah, that's, I mean, it makes it even finer in some sense. Oh, yeah, okay. Out of time, so I'll stop here. I wanted